It's my pleasure to welcome Valerio Pagliari from the Technical University in Vienna at our Necas Continuum Mechanics seminar. So Valerio got his PhD at the University of Pisa in 2019. His advisor was Matteo Novaga. I'm sorry, and Valerio is an expert or is interested in calculus of variations, in particular homogenization theory and mean curvature flows, and this will be also the topic of today's seminar. So Valerio, please.
Thank you very much for the presentation and mostly for the invitation, for giving me this chance to speak about a piece of the research that I carried out when I was a PhD student. So as Martin said, this is something that I studied under the supervision of Matteo Novaga back in the time in Pisa. And as you can see from the title, I would like to speak about some curvatures related problems. So in particular, I will present some convergence results of no local flows to the standard mean curvature flow. So this is the outline of the talk. First of all, I will try to give you a general idea of the problems that I would like to tackle. And then I will try to explain what are the goals that we pursue in this presentation. And since I do not assume that everybody is familiar with the concept that I'm dealing with, I will give you a sort of warm-up about no local functionals, in particular of curvature type. And then we will be ready to address the main results that I want to discuss, which are of two kinds. And as I told you, those are convergence results. So we have this no local functional, and it is quite natural to wonder what is the connection between these no local functionals with their standard counterparts. So we have curvatures functional, no local curvature functional. We will show that we have some kind of convergence toward the local curvature functional. And since as soon as we have curvature functional, we can consider the motion, the related motions, we will investigate whether the relationship that we have for the functional is carried over to the motions. Before I go on, all I'm going to say today is a joint work with Annalisa Cesaroni at the University of Padua. And if you're interested, you can check the paper which has been recently accepted in discrete and continuous dynamical systems.
Yep.
Okay. So we're ready to start. The talk is going to be about geometric motions. So what do I mean by this? Those are a particular kind of Cauchy problems. So somehow PDEs, okay, that describe sets that evolve according to a geometric law. This means that I give you an initial datum E0 in the standard Euclidean space. And then I prescribe that at later times, each point on the boundary of the evolved set is moving with normal velocity equal to the curvature functional of the set at the point that I'm considering. So in this talk, we will focus on two kinds of curvature functional, as I told you. One's going to be the local standard mean curvature, and the other one is going to be a local counterpart of the mean curvature. And so those are the definitions that we need to have in mind during the presentation. So the standard mean curvature, well, we call it mean, even if I'm not averaging. So, but this is customary to call it like this. So this is the mean curvature. What's that? So assume that you have a bounded set. I'm sorry, not bounded, I mean smooth sets. Set with smooth boundary, and we can define point by point on the boundary the outer normal. And we define, as in this formula, the mean curvature of the set. Okay, so this is the divergence, some more or less the divergence of the outer normal, which you can rewrite some manipulation as the trace of the projection on the tangent plane of the Jacobian of the normal. Okay, this is quite classical. And what's instead a non-local curvature? Well, the kind of non-local curvatures that I consider are defined in terms of a positive given kernel K, which somehow you could think of being a sort of weight, okay, that's express some interaction of points in the space. Well, you define the non-local curvature as this integral that you can see here in this formula. So you take the characteristic function of the set E. That means you take a function which is equal to 1 where you need E and equals minus 0, when you need the complement. And you take this sort of balance between points in E and points in the complement of E, and you weight this with the kernel. So in some sense, this idea of balance gives you, in a very approximate way, a measure of how much the set E is deviating from its tangent plane somehow in a very heuristic way. And this is why we call it curvature. And so what's the idea behind my talk? So what are we going to do during this talk? Well, this is a standard thing that you could do. I mean, this is the same thing that you do when you approximate any LP function, for instance. What you do? Well, you consider some sequence of modifiers. The modifiers generally have this property that when you rescale the parameter, they converge toward the Dirac delta in the origin. And this means that when after modification of the given function, you retrieve in the limits the one that you were given initially. And this is the same thing that we're going to do. But in this case, we rescale this kernel K. So we have the kernel K, we consider this kind of rescaling, which is a scaling that preserves somehow the L1 norm. And you consider the non-local curvature associated with the rescaling of the kernel. So this is the same type of function that I considered before, but the only difference is that now instead of K, I have K epsilon, okay? And so the question that I'm going to explore are somehow, I mean, you can imagine them easily. So what is happening as epsilon tends to 0, okay? So the questions are the one that I anticipated. So the first thing, is it true that the curvature functional associated with the rescaled kernel converge to the local one? And if it is the case, can we derive some information about the solutions to the related flows? Okay, so those are the two questions that I'm going to focus on today. But before we deep into the analysis, I would like to give you some more information about these non-local functionals. So a sort of overview, okay? Well, these functionals have recently attracted much attention. So for instance, for people in the community of calculus of variation, you could think of them as being curvatures because they are the first variations of some functional that for some reason we call perimeters. So to be precise, we could consider this non-local energy. So K is as before, is a positive kernel, and you consider this double integral. This double integral is somehow considering the interaction between points of a given set E and the points in its complement. So I mean, if you want to have an heuristic idea, it's easy to imagine that if this is your set E, when you take a point X inside E and a point Y outside, somehow the interaction is crossing the boundary of E, and heuristically, very heuristically, this is giving a sort of measure of the boundary of E in a non-local way. And this is why these functionals are called non-local perimeters. Well, if you take the geometric first variations of this object, which means that if you deform the set E with some sort of local geomorphisms, and you take this geometric variation to become smaller and smaller, where in the limit you compute this first variation, and what you get, well, you get actually the functional hk, which for this reason we could think of a no local curvature, because this is the first variation of something which is called no local perimeter. So there is a very vast literature by now about this kind of no local problems. The first one that considered no local perimeters, and immediately they also associated them with the no local curvature, were Caffarelli, Roquejoffre, and Savin in 2010, which consider a particular class of kernels, those that are known as fractional ones, which means that the kernel is a power law of order minus the dimension of the space minus a fractional parameter, something which is between 0 and 1. Okay, so you have a decay at infinity, which is dimension plus some fractional exponents. And then a result that goes a bit in the direction that I told you before. So this idea of approximating local things by means of no local ones can be found for perimeters in this paper by Ambrosio, De Filipis, and Martinazzi, where they studied the gamma convergence, so a kind of variational convergence of the fractional perimeters to the standard Euclidean perimeter. So the one defined in terms of total variation of BV functions, okay? And then, okay, you could generalize the analysis to more and consider other kind of kernels, not necessarily the fractional one, not necessarily radial kernels. And this is what I partly did during my PhD in these papers that you can see here. Well, okay, but then, so now you see there is a sorry. There is a variational reason to investigate the question that I posed before. So what is the asymptotic for the curve versus functional? Because we know that for a perimeter, the asymptotic reasoning somehow works, okay? But then now I'm speaking at seminar on continuum mechanics, and there is also some continuum mechanic background on these no local functionals. So actually, the very first time that these no local functionals, or to be more precise, these no local Hamilton-Jacobi equations, okay, to be more precise, appeared in the literature, it was because they were considered as good models to describe dislocation dynamics. So I do not claim to be an expert on the field, but I think it's nevertheless interesting to give you an idea, okay, a hint. So you know that the macroscopic phenomenon of plasticity in metals is explained by a microscopic theory, which is the theory of dislocations. So dislocations are misalignments in the periodic structure of a crystal. And each dislocation produces an elastic field. So you have a force, okay, acting on other points in the crystal, loosely speaking. And this force is known as the Pitch-Keller force. But what is interesting for us at the point is that some authors proposed to model the Pitch-Keller force by means of convolution kernels. So you have these no-locality features appearing, okay? So to be precise, the first ones to propose such models were Alvarez, Hochler, Lebois, and Monod in this paper, where they proposed to describe dislocation dynamics by means of a no-local Hamilton-Jacobi equation. This means that you have some sort of parabolic equation. So you have a time derivative which you equal to an Hamiltonian, and this Hamiltonian features this convolution kernel, okay, more or less. This is the idea. Then, now, since you're dealing, maybe you know this better than me, when you want to deal with something which is a physical model, somehow you're facing a hard time because you need to keep track of too many things. So in time, the model to be more manageable in mathematical terms, but somehow simplified. And this is why I put here some dots, because there's a quite long list of authors that modified a bit the initial model. And as far as our analysis is concerned, I would just like to point out this single paper, this single contribution by Dalio, Forcadell, and Monod, where the authors consider the large scale limit of a dislocation dynamic model. So what did they do? They consider this motion by a non-local Hamilton-Jacobi equation. So pretty much in the spirit of what I'm going to tell you next. And the idea is to rescale the kernels that gives the contribution, because according to the scale parameter in the model, because you have some physics behind, so there is some scale parameter. And so what's happening from, say, a mesoscope, they analyze somehow what is happening if you go to the mesoscopic level to the macroscopic level, taking this scale parameter to 0. And what did they prove? Well, they proved that this non-local Hamilton-Jacobi equation, the solution of this non-local Hamilton-Jacobi equation, start converging to the solution of a mean curvature flow. So this is somehow a sort of precursor of what I'm going to tell you next. But in their case, okay, in their model, this is a technical but important difference for us, is that the convolution kernel that they consider was non-singular, okay? So you don't have any singularity in the origin. Later, Ambert managed to deal also with the singular case, so he proposed a model for motion by non-local curvature, which feature a singular kernel, namely a fractional kernel. But moreover, there is another important feature of this paper by Ambert, is that he realized that the law exploited to describe dislocation dynamics is indeed, you can understand this as a motion by non-local curvature. So somehow he built, okay, he suggested that the operator that feeds the dislocation dynamics is a non-local curvature operator. Okay, so this is more or less the background for our analysis. And now let us go to the technical part somehow. Let us go to our results. So as I told you, we divide the analysis into 2 steps. Okay, we have our curvature functionals. We first consider the asymptotics of the rescaled non-local curvature functional, and we investigate whether they converge to some local curvature. As you can imagine, the answer is positive, of course, otherwise I won't be speaking here. And then we investigate whether this convergence of the curvature functional is robust enough to yield some information on the solution of the related motion by curvature. Okay, very good. So this is first question 1. We tackle the convergence of the curvature functional. We consider this local functional hk epsilon, so with the scalings that rescaling that I told you before. And this is the question: what is happening when epsilon, the scaling parameter, tends to 0? Now, of course, here the thing is a bit vague, because I haven't told you much about this kernel K. I simply told you that it is a positive kernel. Well, of course, we need to require some more structural assumption on it, and this is where our analysis departs from the ones that was already there somehow. So first of all, okay, we're assuming K to be even. Somehow this is reasonable, having in mind the variational origin of the curvature that I told you before. But we don't assume our kernel to be L1. So it will allow for some singularity in the origin. And so this is this second condition here. We require our kernel to be L1 outside of bolts close to the origin. Okay, outside of ball centered at the origin, excuse me. And then we require a further integrability assumption, which is we assume that on this sort of butterfly region here, so the region comprised by these two parabolas with axis along the direction E, the kernel has finite integral. And this might seem a bit strange, but actually it allows our curvature functional to be finite on sets which have a C11 boundary. Now, as I told you, since we do not assume our kernel to be L1, of course, here we need to modify a bit the definition of curvature, because in principle, this integral over RD might not be convergent. So we need to remove a small ball close to the origin and then take the limit as the radius of the balls tend to 0. This is why we get this principal value here, but this is a technical thing, okay? And then in our research, we needed also to assume some other technical aspects on the kernel K, some decay assumptions, of course, because we need, so of course, we're dealing with a local model. When we rescale the parameter as to concentrate the mass of the kernel close to the origin, you want that what's happening far from the origin, so what happens in the tails of your kernel, is negligible. So you imagine that you need to require some decay assumptions on the kernel, but I'm not listening it in detail here. But you will believe that the things that I tell you are hopefully true. Okay, so the important thing, the bottom line of this slide is, okay, if your set is regular enough, well, the non-local curvature is finite. This lays a bit the ground for the first result that I present you. So if I give you a set with smooth boundary, then you have convergence of the non-local functionals, the rescaling non-local functional, up to a further rescaling parameter here, 1 over epsilon. And you have convergence to the standard mean curvature up to a multiplicative constant, which depends on the dimension and on the kernel K, of course. And you will believe me, if your boundary is compact, you can patch things together and get a uniform convergence in X. Now, just for the sake of simplicity here, I'm writing what's happened just when K is radial. Our analysis allows us to take on also the non-radial case, but I mean, the formulas get a bit more complicated, so it doesn't change the central point of our analysis. Okay, so we could allow for non-radial kernels. Very good. Now, as I told you, our analysis is dealing with some non-local kernels, which is in contrast to what Dalio, Forcadell, and Monod did. And also another difference is that, okay, they're dealing with a model from dislocation dynamics. And you know from the theory of dislocation dynamics that your kernel needs to have a particular decay at infinity. In particular, in their case, so if you are in general dimension D, you need your kernel to decay as 1 over the power of X power D plus 1. D plus 1, okay? So this means that, and it's a different decay from the one that we consider in our work, which I haven't said explicitly, but it's a different decay. And in particular, for these reasons, also the scaling that Dalio, Forcadell, and Monod consider is necessarily different from ours. So they need, instead of just having 1 over epsilon, they need to add a logarithmic correction, which is typical of dislocation theory somehow. Okay. Then we also, previous to our results, we also had some contribution dealing with the fractional case. So Amber already suggested that there could have been a convergence of the non-local fractional curvatures to the local one. This was thoroughly addressed by Abatangelo and Baldinoci. And then some other consideration in the same spirit was carried out by Mazzon, Rossi, and Toledo later for L1, so non-singular and radial kernels. Okay, so somehow what we did was to consider, so to broaden a bit the spectrum somehow of kernels encompassing the analysis. But so in this, okay, in the works by Amber, Abatangelo, Valdinoci, and in the one by Mazzon, there is no connection between the convergence of the functionals and of the related flows. Okay, and instead in this case, okay, there is this relation between the convergence of the curvatures and of the flows, but the kernel is non-singular. Okay, so our work is a bit different from the things that were already there. And sorry, this is the wrong direction. Okay, very good. So we're done as far as the first question is concerned. We can move to the second issue here. So this is the convergence of the flows related to the curvature functional. So I recall you what we are considering. So if you have a point xt, okay, which is on the boundary of at time t, well, we prescribe that its normal velocity, this is just a sort of shorthand, okay, I'm going to be more precise in a while, okay, you prescribe that the normal velocity of the point x on the boundary of B equals some curvature, local or non-local, of the set T at the point x, and you prescribe some initial condition, okay. And now the question is, what happens for the solutions to these problems as epsilon tends to 0? It's quite easy to understand what we want to do, but so you know that when we deal with motion by curvature, we need to be a bit precise about the notion of solution that we consider, because it's well known that for instance, classical solutions to curvature, to motions by curvature, develop singularities in finite time. Okay, so you cannot hope. I mean, you could also do the analysis for smooth flows, for smooth flows, but you know that you don't have global existence in time. So you need to go to some weak. This is the reason why it was considered some weak notions of solutions to motions by curvature were considered, and we are going. There are some among which one could choose. We go for the strategy that is normally used to deal with Hamilton-Jacobi equations. As I told you, this non-local functional came from the theory of non-local Hamilton-Jacobi equations. So we somehow take the same framework from that theory. And so we work in the level set formulations, okay, of our flows. What does it mean? It means that we assume our set E to be the super level set of some function U, which we could assume for the moment to be regular, so that we can make the computation and write something, a meaningful equation. So if you go there and you do the substitution that you need to do, you get that the local, when you have the, so when you have H, the local curvature, the mean curvature, the equation that you get for U is this one. And this other is the one that you get for the no-local flow, okay? So we're going to consider weak solutions to these two PDEs, okay, to these two parabolic PDEs. And okay, so this is a sort of recap. What is the weak notion that I'm considering? This is the notion of viscosity solution. So you know that viscosity solution are nice. Why are they nice? Why do we like viscosity solution? Well, because they allow you to go past of singularities, because they allow for existence results that are global in time. Okay. Then they lead to well-posedness in the sense that you have uniqueness, and this due to the fact that you're considering equations which have some monotonicity. Okay. And they grant some kind of regularity if you start, for instance, Lipschitz continuity, if you start from Lipschitz datum or from a Lipschitz datum. And then at least for the classical problems, it is well known that you have consistency with the classical solution as long as the ladder exists. Okay, so this is some bibliography about this theory of viscosity solution for geometric, for curvature flows. So it's 30 years by now that we know that viscosity solution are a good tool to analyze mean curvature flows. This goes back to the works by Evans and Sprague, Chengig and Goto. Then it's a bit more recent, the treatment of no-local equations in the same framework. It goes back to the contribution by Slepchev, and for the fractional case, so for when the kernel is singular, to the work by Ambert that I mentioned to you previously. And let me tell you that a more recent contribution is the one by Chambol, Morin, and Pontiglione, where they somehow developed a sort of axiomatic theory for motions by curvature. They gave some requirement that some functional, some abstract functional that we call curvature needs to satisfy in order to have well-posed nest for the related level set formulation, no matter if the curvature is local or non-local. So this is why I call it unified framework. Okay. And very good. So let me recall you once more what we have so far. So we have our kernel K. We have our non-local curvature functionals. We consider the one associated with the rescaled kernel. And we know that we have convergence of the curvature functionals, okay? And we know that the convergence is uniform if we are on a compact boundary. Okay. Then we take an initial datum, which we assume to be Lipschitz and somehow well localized, so constant outside of complex sets. Okay. We consider the solution, the viscosity solution to the level set formulation of the local problem. We consider the viscosity solutions to the to the epsilon non-local problem. So this is this one. Actually, of course, here you see there is a sort of rescaling that I need to do in order to get precise. I mean, because here I have this constant, I need to divide both sides so I to grant consistency. Okay, this is a minor thing, of course. Well, the main result is that the sequence, the family of viscosity solution to the epsilon non-local problem locally uniformly converges to the solution of the local problem as epsilon tends to 0. Okay, this is the main results of the work we did with Annalisa. And in the next slides, I would like to give you some ideas about the tools. Because, so as I told you, our work is somehow similar to things that were already there. But it's nice to see that, I mean, you can be a fantasy and use different tools from the people before. And this is why I'm going to give you some ideas about the proof, which is somehow, I would say, original. So, I said, we consider for each epsilon, we consider the viscosity solution to the Cauchy problem for the non-local curvature motion. Okay. The first thing, okay, you want to say, they converge to something. The first thing you do, maybe you could wonder, okay, but do you have any candidate limits? So what you do, you prove that you have some a priori bounds. This means some compactness for the sequence, okay? And how do you do so? Well, you can prove, this is somehow standard in the theory of viscosity solution, I could say. You prove some equi-Hölder and equi-Lipschitz property of these solutions. Okay, this means that up to subsequences, you have some candidate limits, okay, which I denote by V. Very good. Now, I want to prove that whatever is the accumulation point for the sequence U epsilon that you ended up with, well, this coincides actually with the solution with the viscosity solution of the local problem. Okay. If this is the case, I'm done. I've concluded the proof. Okay. How do we prove this thing? This is okay. This is the a recap of the goal of the next slides. Okay, I have a cluster point of the sequence of viscosity solutions to the non-local flows. I want to prove that this no matter what the cluster point, it coincides with the viscosity solution of the local flow. We use this sort of set theoretic approach. So we consider these upper limits defined in a set theoretic sense. Okay, so I mean, instead of having a limp soup, you first take the union of this super level set, and then you take an intersection. And you firstly do it with strict inequality for, say, strict, so to say, super level set, and also with large super level sets. This has to do with the fact that you, since I mean, you're considering the level set formulation, it means that you do not always control. If you control just what is happening with the strict super level set, it's not to be taken for granted that you also know what's happening when you take the closure. It could be that where the set where you have equality is fat, as it is a technical word indeed. The fattening phenomenon is something that which is well known in the framework of geometric evolutions. Okay, and okay, we consider this sort of set theoretic upper limits, and what do? We want to prove some sort of chain of inclusions. Okay, so we consider the strict super level set of the cluster point. Okay, and of course this is smaller. Okay, than the set where you have the large inequality. We want to prove that you can put these upper limits inside, so the strict one and the large one. Okay, oh, sorry, oh no, very bad, excuse me. Okay, should be here. Okay, excuse me for the technical problem. Okay, so what I was saying, okay, we want to prove this inclusion between these sets, and we want to improve. We want to prove the same chain of inclusions with the super level sets of the viscosity solution of the local problem. Well, why we want to do so? Because if you have both of this chain of inequality, of this chain of inclusions holding, then you will find that the strict superlevel set of V is included in the large superlevel set of U. And conversely, you will have that the strict superlevel set of U is contained in the large superlevel set of V. And this implies that the functions U and V coincide. This is a sort of corollary, small corollary of these inclusions. Okay, so this is what we want to prove. And how do we get these inclusions? Well, for the first one is somehow easy because we already know we are assuming that we have even uniform convergence of the U epsilon to V. So for this one, it's enough to have pointwise convergence. We even have more, so we're happier. Okay, but for the second chain of inclusions, we will use the first result that I presented to you. So the uniform convergence of the curvatures functional. We will use this convergence of the curvature functional in relation to the theory of geometric barriers. So this is a technical tool that I need to introduce to you now. And this is different from what was already there in the literature. So, as I told you, our approach is grounded on the theory of geometric barriers. What's a barrier? We start with this notion of geometric subsolution. So, a motion by curvature is something where here you have equality holding. A strict geometric subsolution is a flow of sets a flow which is a smooth flow, okay, in time and space, such that you have strict inequality here, okay, very easy. So this is a strict geometric subsolution to the flow, and here it could be curvature. Here means it could be the non-local or the local one, doesn't matter at this stage. Okay, then in the 90s, Ennio De Giorgi introduced this concept of geometric barrier, which is a sort of another concept of weak solution, okay, somehow to evolution problems. What's a barrier? So basically, you still have a law that at each time t associates a set E. You call E a barrier with respect to the family of all strict geometric subsolution if whenever you take a strict geometric subsolution such that at the initial time you have this inclusion, so the smooth subsolution is smaller, is included in the candidate barrier, then the same inclusion also holds at later times. Okay, so an outer barrier is something such that inclusions with strict geometric subsolution is preserved as time passes by. Okay, this is this notion, this set theoretic notion. Okay, and why do we care about this concept? Because it's comparable to the one of viscosity solution. But since here we're dealing with sets, so this is a sort of things that we translate from one language to the other. So curvatures are given in terms of sets, okay? So it's easy to deal with curvatures if you're working on sets. But on the other hand, the solution that we have are given in terms of given in terms of viscosity theory. So if we can bridge viscosity theory with sets, then we're quite happy because we can make the things speak together. Okay, and this is what we do, or actually what some other people did before us. There were some work of the late 90s and by Bellettini and Novaga, which explored the connection between this concept of barrier and the one of viscosity solution. What did they prove? Well, they proved that if U is the viscosity solution to the local flow, so to the standard mean curvature flow, the superlevel sets of the solution are the minimal outer barrier with respect to strict geometric subsolution. And what I mean minimal, I mean that any other barrier includes them, okay? So it is a ordering in terms of inclusion of sets, okay? Then later there was more attention. I mean, these non-local flows were studied as well. So it was somehow natural to wonder what's happening for barriers in this non-local setting. And then this is the result that Annalisa with some other collaborators proved some years ago. If you take a viscosity solution to the non-local problem, then the superlevel set, the strict superlevel set of the solution is an outer barrier for the strict geometric subsolution, but now to the non-local problem. Okay, so the thing that we need to do is we need to relate the strict geometric subsolution of the local problem to the one of the non-local problem. And this is what we do in this following line. So we start with a strict geometric subsolution to the local flow. So let me recall you. So what do? We take a family of sets which is evolving, satisfying this inequality. Okay, so the curvature, the sets D evolve, and at each time their normal velocity is strictly smaller than the curvature of the set at a given point. Okay, and in this case we consider as the curvature functional the local one. Okay, so D is a strict geometric subsolution to the local flow. Okay, but then what do we know? We exploit, sorry again for this going back and forth, we exploit again, okay, Okay, here's the slide. We exploit again the fact that here we have a sort of gap. We have strict inequality. Okay, so we can exploit the uniform convergence of the curvatures functional, the first result that we proved, to substitute the local curvature functional with the non-local curvature functionals. So we find that D is also a strict geometric subsolution for the non-local problems for all epsilon sufficiently small. Okay. Below a certain threshold, D is a strict geometric subsolution for all epsilon. Very good. And then we use these results about comparison between viscosity solution and barriers for no local flows. So we know that each of these super level sets is an outer barrier. We can take, since we have some something which is holding for all epsilon small enough, we can take the set theoretic upper limit to deduce that this set, the set theoretic upper limit is still an outer barrier. But now we started for something which was a strict geometric subsolution to the local flow. So here we have an outer barrier for the local flow. Okay, well, and now we're ready to conclude, because we know that the super level set of the viscosity solution to the local flow is the minimal barrier. So if this guy here is an outer barrier, then it must include the super level set of the set Q. Okay, and now we're done, because I recall you, this was exactly the inclusion that I wanted to prove, this one. And so as for the other inclusions, well, we need to go with, you can imagine it, you need to reverse inequalities. So here you will speak about strict geometric super solutions. You will speak about inner barriers. Then you have some, also if the connection helps, okay, you will speak about strict geometric super solution. You will speak about inner barriers, and you will have as well some comparison results, and you would conclude the other inclusion that you need. So with that, this was the approach that we used. Let me tell you as a very concluding remark that this was different from the things that were already there in the literature, because I mean, you're dealing in the, you're working in the theory of in the framework of the theory of viscosity solutions. So you could simply take follow the same streamline of ideas and take some limits of the viscosity solution, so some perturbed test function argument, and conclude the same result. This is different. Our approach was different because we use something which is more set theoretic. Okay, so the very last slide. So what did we do? So we consider this notion of no local curvature, and we showed up that in a somehow blow up limits, in a scaling limits, you can recover the classical mean curvature. And our analysis also includes some anisotropic functionals, can allow for anisotropies. Okay, and this convergence is sufficiently robust to ensure that the result is inherited by the solutions to the geometric flows associated with the curvatures. So you have that the solution, the viscosity solutions of the local geometric flow converge locally uniformly to the solution of the viscosity solution of the local motion by curvature. And the key point in our approach is that we use this somehow a bit unknown, I can say, I imagine a bit unknown theory of geometric barrier. Okay, so that's all on my side. I hope you enjoyed, and I thank you for your attention. I'm open up for questions, if any.